When you watch a magnet act on iron filings, you are witnessing millions of tiny particles snapping into a highly organized geometric pattern. Beneath that macroscopic behavior is a complex microscopic reality. A magnetic material is composed of a massive lattice of individual atomic spins, all constantly shifting and interacting as magnetic dipoles. This graphic illustrates the core mathematical problem. To calculate the exact magnetic field acting on just one target spin, you have to track the orientation of every single surrounding neighbor in the lattice. Look at the exact field dependence equation on the right. The target spin reacts to the sum of all neighbor interactions. For a macroscopic piece of iron, calculating this requires evaluating 2 to the power of n microstates. Predicting the thermodynamic states of a bulk magnetic material using exact microscopic interactions is mathematically impossible. The physics demands a shortcut. In 1907, physicist Pierre Ernest Weiss proposed a radical way to bypass this computational roadblock. This diagram shows his solution, the mean field approximation. Instead of tracking the chaotic, shifting web of exact spin-to-spin interactions, Weiss replaced that entire local environment with a single, stable, average internal field. The total effective field felt by a spin becomes a simple addition equation: any applied external magnetic field plus this new approximated internal mean field. We can dissect this internal field further. This graphic isolates the Weiss molecular field equation. The mean field is calculated by multiplying lambda, a constant measuring the strength of the magnetic interactions, by m, the total average magnetization of the volume. The individual spin is no longer reacting to its specific physical neighbors. It is reacting to a proportional influence of the average state of the entire material. By substituting an average for the specific, Weiss collapsed an intractable n-body problem into a solvable single-body problem, paving the way for predictive thermodynamics. How does a piece of iron become spontaneously magnetic below a critical temperature, even when there is absolutely zero external magnetic field acting upon it? Mean field theory answers this by describing a positive mathematical feedback loop. This diagram maps the cycle. In steps 1 and 2, a tiny spontaneous alignment of spins appears due to random thermal fluctuations. That initial alignment immediately generates a small internal mean field. Moving to steps 3 and 4, this internal field forces even more surrounding spins to align with it. That increases the overall magnetization, which in turn strengthens the internal field even further. At high temperatures, thermal disorder rips this alignment apart. But below a specific threshold, the critical temperature, this runaway positive feedback overcomes the thermal disorder and locks the material into a ferromagnetic state. This feedback mechanism proves that a material can bootstrap its own magnetic order purely through self-consistency. To prove this mathematically, physicists apply the conceptual Weiss field to a strict discrete quantum framework, the Ising model. This graphic demonstrates the translation. At the top is the exact Ising Hamiltonian, tracking individual discrete spin states. We apply the mean field hack, replacing the precise discrete states of neighboring spins, S sub j, with their continuous thermal average, represented by m. That substitution collapses the exact sum into the clean effective field equation at the bottom. A spin now feels a local field determined by the external field, the interaction strength J, and Z, its number of nearest neighbors.
This logic leads directly to the core mathematical engine that enforces magnetic order, the central self-consistency equation, visualized here as a balance scale. The assumed average spin, m, on the left side of the equation must exactly equal the thermodynamic response it generates on the right side, dictated by the hyperbolic tangent function. A phase transition only occurs when the mathematical model finds this precise equilibrium. The theory successfully turns a chaotic physical process of billions of interacting particles into an elegant algebraic root-finding problem. We can also scale up, connecting the microscopic self-consistency of individual spins to the macroscopic thermodynamics of the entire material. This pair of graphs illustrates Landau theory, which visualizes the ordering process as an energy landscape based on free energy. Look at the graph on the left. Above the critical temperature, thermal energy dominates. The material has a single stable minimum at the bottom of the parabola, where the overall magnetization is exactly 0. Now look at the right graph. Below the critical temperature, spontaneous symmetry breaking occurs. The curve shifts into a double well. The system can no longer stay at 0. It falls into one of the two stable ordered states, taking on a positive or negative overall magnetization. Minimizing this macroscopic free energy curve yields the exact same physical result as solving the microscopic self-consistency equation. Despite its algebraic elegance, mean field theory has a strict limitation. When predicting the exact temperature where these phase transitions occur, it systematically fails. The culprit behind this failure is the very average assumption that made the math possible. This graphic details the blind spot. Examine the grid on the left. In physical reality, spins form tight local clusters. A block might have an intense pocket of spins pointing up and another pocket pointing down. Because the overall mathematical average of that specific block evaluates to 0, mean field theory assumes 0 interactions are happening. It completely misses the localized domain wall physics occurring inside. Compare the formulas on the right. By ignoring localized thermal fluctuations, mean field theory predicts a critical temperature of 4J for a two-dimensional square lattice. The exact 2D reality, solved by Lars Onsager, proves the structure is much less stable, transitioning at roughly 2.269J. By smearing out local spatial reality into a perfectly uniform background, the theory assumes that organizing the system is much easier than it actually is. If mean field theory reliably overestimates critical temperatures and ignores spatial reality, why is it still a cornerstone of solid-state physics? This table defines the boundaries of the theory, addressing the common misconceptions about its purpose. Look at reality number 2. The molecular field isn't an ordinary magnetic field sitting inside the material. It is a mathematical proxy, an effective field representing collective quantum interactions. And as reality 4 establishes, the goal is not numerical precision. The theory perfectly captures the qualitative mechanism of cooperative magnetic order. Physics relies on building approximations. You must establish the smooth, idealized baseline of a system before you can calculate its chaotic, localized fluctuations. Mean field theory is not the final answer to magnetism. It is the essential conceptual bridge that takes the intractable geometry of the universe and makes it mathematically accessible.